Hello, calculus students. This is Mr. Allen here. Today we are going to begin Chapter 3. So Chapter 2 was on basically finding derivatives. What is a derivative and how do we find the derivatives? There was a little bit of applications at the end when we talked about related rates. But this chapter, Chapter 3, is truly the applications of integral or of derivatives. In other words, what do derivatives do for us in terms of applications? So today we're going to look at something called extrema on an interval. We have three objectives here. We want to understand the definition of extrema of a function on an interval. We want to understand the definition of a relative extrema on a function on an open interval. And finally, extrema on a closed interval. So in calculus, much effort is devoted to determining the behavior of a function on an interval. Does the function f have a maximum on an interval? Does it have a minimum? Is the function increasing? Where is it decreasing? In this chapter, you're going to learn how to use derivatives to answer these questions. So first, let's talk about what the definition is of an extrema. Extrema sounds like a really fancy word, and it just means extreme. So let f be defined on the interval I containing c. F of c is called the minimum of f on the interval I if f of c is less than or equal to all of the f of x's on that interval, which kind of makes sense. If it's less than or equal to all of the other values of that function, then that's called a minimum. A maximum, just the opposite. F of c is called a maximum on an interval if f of c is greater than or equal to all of the x's on that interval. These are called extreme values, or extrema for singular, or extrema is plural, and singular is extrema. I use the word extreme. Absolute minimums, absolute maximums, global mins, global maximums, those are the same thing. So an absolute minimum means it's literally the lowest value for the entire function. So here we've got two pictures. We've got figure 3.1 point A and figure 3.1 point B. And I want you to look carefully. Both of these functions are on the interval from 1 to 2. It's just the second function here, 3.1b, is on the open interval. Notice that both functions are continuous and differentiable. Now I claim the function on the left has a minimum, a lowest point, if you will, and so does the one on the right, and those two have the lowest point of -1. In other words, the minimum is, I'm sorry, I said -1, is 1 when x is 0. However, the function on the left has a maximum at 5 at x equals 2, and you can clearly see the dot label there is a closed dot with 2. Notice that the function on the right, though, does not have a maximum. And the reason it does not have a maximum is because that dot is open. That point, 2, 5, does not exist there. Now, students sometimes start thinking, well, but Mr. Allen, what about, the point 1.999, which would give us 4.999? If you understand what a limit is, remember, a limit is a predicted y value. You can find no such y value at 5 there. So this one has no maximum. So moreover, figure 3.1c, which is what we're looking at here, this one's even different still. So notice that this is on the closed interval again, but now look at x equals 0. So what we've done here is we've made this into like a piecewise defined function where we define f of 0 to be 2. This function has a maximum at 2, 5, like 3.1a did, but now it has no minimum. There is no lowest value for this function. Now it does have a limit, but we do not have an absolute lowest value. So let's look at theorem 3.1 here at the bottom of the page. This is an important theorem. You will see me, or you will hear me talk about it as EVT, the extreme value theorem. And it says the following: if f is continuous on a closed interval AB, then f has both a minimum and a maximum on that interval. So notice I said continuous on the closed interval. In this example here, it was not continuous at 0, therefore it doesn't have a minimum in this case. If we look back at the previous slide, we can see here that it is not on a closed interval, therefore it does not have a maximum in this case. However, if we look at our first example, this function is continuous on the closed interval. It has a highest point and it has a lowest point. So here's more common function that we might see, and this is the function x cubed minus 3x squared. And we can see that it has a relative maximum, that would be right here, and it has a relative minimum. Now we're using the words relative, here, because this function tends to infinity as x goes to infinity. So it actually has no absolute maximum, but it has a relative maximum. By the way, another word you might see in textbooks or on exams is local maximum. So if we think about that as being local to this portion of the graph, not the whole graph, you would say that that's, another word we might use is that's a hill. That is a relative maximum. Down here, we have a relative minimum or a local minimum. So we can think of relative maximums as occurring at hills on graphs and relative minimums as valleys. Such a hill and a valley can occur in two ways. If the hill or the valley is smooth and rounded, then the graph has a horizontal tangent line. And by the way, if it has a horizontal tangent line, that tells us that the slope or the derivative of that value is equal to 0, which we'll talk more about in a second. The second situation we can have a high point or a low point is if we have a sharp turn or a peak. Here the function's not going to be differentiable. So in other words, what I'm saying is f prime of c is equal to d8. We talked about that in chapter 1. All right, so this is an important slide, definition of a relative extrema. If there's an open interval containing c for which f of c is a maximum, then it is called a relative maximum. Or we say it's a relative maximum at blah, blah, blah. Similarly, if there's an open interval containing c for which f of c is a minimum, we call it a relative minimum. The plural of relative maximum and a relative minimum is, the plural of relative maximum is relative maxima. That means you have multiple relative maximums, and then of course relative minima. Again, I already kind of mentioned this on the previous slide, is local max and local. So now I'm going to do one example here with 3 parts. So we're going to find the relative max of this one, we're going to find the relative min of this one, and we're going to find the relative max of this guy here, and the min. So let's look at example A. So we've got the function here, f of x equals 9 parenthesis x squared minus 3 over x cubed. If we differentiate this using our quotient rule, which is low d high minus high d low over low low, we get the following. Now what we want to do is just clean it up a little bit, and this one cleans up quite a bit. So now here's the key idea. This goes back to what I said a couple of slides ago. At the point 3,2, the value of the derivative, that would be an x value of 3, is 0. In other words, there's a horizontal tangent line. Interesting. So it turns out that there is a relative maximum at the point 3,2. And just coincidentally, and it's not a coincidence, f prime of 3 was 0. Let's look at another example. So here we've got the absolute value function. This one's always a little bit difficult for students to understand, so please pay particular attention to this one. So here's the graph. I've already got the graph right here. Now clearly you can see that it's got a relative minimum there. But what I want you to notice is look at the one-sided limits. So let's look at the limit of this function on the left. And what I'm doing is actually I'm doing the slope formula, the formal definition for derivative one-sided. So we did some examples of this in chapter 1. So I'm using the difference quotient. I'm using the alternative definition for slope of the tangent line. Goes all the way back. Actually, I'm sorry. We did one-side limits in chapter 1. This is in section 2.1 though that we used this particular definition for finding slopes of tangent. Anyways, so when you find the slope of this tangent line right here, well, it turns out to be -1, which is kind of a no-brainer because it's linear. So what's the slope of the tangent line going to be over here on this side? Well, of course, the slope of the tangent line on the right side is going to be 1. So the limit on the left is -1, the limit on the right is +1, and so guess what we can conclude? F prime of 0 equals D and E. Because remember, a derivative is a limit, and if the limit on the left doesn't match the limit on the right, then the derivative doesn't exist there. So what I'm trying to illustrate here is this function has a relative minimum at 0, 0, and that f prime of 0 did not exist. And let's go ahead and look at sine. So if we do the derivative of sine, we get cosine. So I've graphed here, this is sine. And now if we think about right at this point here, this would be one of those hills, right? So the horizontal tangent line would be there. So what is the value of cosine, which is the derivative, the cosine of pi over 2? Well, I hope you recall that the cosine of pi over 2 is 0. The cosine of pi over 2 is 0. What about the cosine of 3 pi over 2? Well, that's also 0. Again, you're going to get another horizontal tangent line there. So this is a relative maximum for the sine function, and then this is a relative minimum. I'm going to clear off all that ink so you can see that a little bit better. So I've done 3 examples where we've talked about those hills and valleys, or those peaks or valleys, and we've seen that in each of the cases the derivative was equal to 0 or D and E, which leads us to something called critical numbers. This is something that you will be asked to do in the future, and it's critical because, well, I'll show you why it's critical. Hopefully it'll make sense why it's critical. Note that in example 1 that each relative extrema, the derivative was either 0 or D and E. The x values at these special points are called critical numbers. So notice right here we've got f prime equals D and E, and right here we have f prime is equal to 0. That leads us to our definition of a critical number. Let f be defined at C if if f prime of C is 0, or, and I'll write this a different way, if f prime of C equals D and E, then we call C a critical number. Now, why are critical numbers important? Well, that's by theorem 3.2, and here's what it says. If f has a relative min or a relative max at x equals c, then it had to happen at a critical number. In other words, what I'm saying is, if you're trying to find relative extrema of a function, the first thing you need to do is determine the critical numbers. Remember, a function has infinitely many points on it. You do not want to check infinitely many points. You only need to check the critical numbers. Now notice, this says if it's a relative min or max, then it happens at a critical number. This does not imply that a critical number guarantees you to have a relative min or max. So here are our guidelines. Number 1, for finding extrema. Find the critical numbers of the function on the open interval. Evaluate the function at each critical number. Evaluate the value of the function at the endpoints, and then the least of these values is going to be the minimum. And by the way, I should note, this is on a closed interval. This is on a closed interval, and the greatest will be the max. So let's look at an example. This will be the last example we'll do, and we'll call it a day. So we've talked about a lot of things. Make sure you read your directions carefully on the problems, and you might need to re-watch this video, or maybe even look at some other examples that are on the online textbook. So we want to find that, now it says extrema. Since it says extrema, that implies we're talking about, it could be absolute, it could be relative, or it could be both. So we have this function here. We're doing it on the closed interval of -1 to 2. Now the first thing I'd like to point out is that this function is continuous on this closed interval, so I'm guaranteeing you that it has an absolute min and an absolute max on this interval. So the first thing we want to do, and by the way, we could go back to our guidelines right here, is we are going to differentiate this function. So here's our original function. We do the derivative using the power rule. We get 12x to the third minus 12x squared. Then what we're going to do is we're going to set this equal to 0. This is a very important step. We're setting this equal, by the way, the reason we're not setting this to D and E is because this function is smooth. So we set it equal to 0, the derivative that is, and then we can factor the left-hand side, and then we can use our zero product property. So we can clearly see that when this is 0, then the whole thing is 0, and when this is 1, the whole thing is 0. So those are critical numbers. So that tells us the only two x values where we could have a relative min or a relative max are at 0 and 1. Now before we go too much further, I want to go back to our guidelines. So number 1 is to find the critical numbers, which we did. Now step number 2, we're going to evaluate those critical numbers, and we're also going to evaluate the endpoints since we're doing this on a closed interval. Okay, so we got our critical numbers of 0, 1, 0, and 1. Because f prime is defined for all x, we can conclude that these are the only critical numbers. Now, we got 0 and 1 for our critical numbers, correct? However, step 3 tells us that we also need to check those endpoints. We need to check the endpoint of -1 because that's where it started, and we also need to check the endpoint of 2. So at this endpoint, we got a value of 7. At this endpoint, we got a value of 16. We get a 0 for our first critical number, and we got a -1 for our second critical number. Notice that -1 is less than any of the other numbers, so it is the minimum, and 16 is the maximum. So here's a picture of this particular graph. This is the 3x to the 4th minus 4x cubed. Here's the graph. We just saw in the last slide that we had the maximum at 216. And then we saw that we had this minimum here at 1, -1. I think that's it. In the figure 3.5, note that the critical number 0 did not yield a relative min or a relative max. So that's just something else we wanted to mention. Oh yeah, so I already kind of mentioned this too. Sorry. In other words, critical numbers of a function do not produce relative extrema. However, if there's a relative extrema, it has to be where there's a critical number. That'll wrap it up. Thank you for watching. Have a good day.